Okay, next, I want to talk about the equilibrium states of systems. Now, we've been talking about the different equilibrias throughout the course so far. So let me briefly summarize the ones we have been discussing and the new ones that I would like to introduce now. So the ones that we have been discussing are, so equilibria that we have been studied. The first one was called thermal equilibrium. So two systems are said to be in thermal equilibrium with each other when the temperatures of the two systems are the same, and there is no flow of heat energy. So thermal equilibrium, we know, happens when temperature remains the same between the two systems. Number two, we have discussed mechanical equilibrium. And mechanical equilibrium, and a system is said to be in mechanical equilibrium when their pressures are the same and there is no exchange of volume. So the thermodynamical identity that is the same is pressure, and there is no exchange of volume. So here it was no flow of heat, and here is no exchange of volume. Now, the next question is, what happens when there is no flow of particles? Now, in this case, we will introduce a new equilibrium, which I'm going to call diffusive equilibrium. And in this case, there is no flow of particles. No flow of particles. So I have not given you an actual thermodynamical identity. We will get to that in a second. Now, before we move on, I want to give you the physical meaning of equilibria. So number one, what happens when you have a thermal equilibrium? You know that the energy flows from a system of the higher value of temperature to the system at lower temperature. This energy will continuously transfer until both systems attain the same temperature, and thermal equilibrium is reached. So hence we can say that the physical meaning of temperature is the tendency of the system to give up energy. So temperature is the tendency of a system to give energy. Now, what about mechanical equilibrium? So volume tends to be transferred from a system with a higher value of pressure to a system with a lower value of pressure. So this value continues until P1 and P2 become equal, and mechanical equilibrium is reached. So then we can say that the physical meaning of pressure is the tendency of the system to take volume. So number two, the physical meaning of pressure is the tendency of a system to take volume. Now I'm going to leave the physical meaning of diffuse equilibrium until I introduce you to the thermodynamical identity for the diffusive equilibrium. So the thermodynamical identity of the diffusive equilibrium is called the chemical potential. And it is denoted as mu. So what is the physical meaning of mu? So we know that particles tend to flow from a system at a higher value of the number of particles or higher chemical potential to a system of low chemical potential. This transfer will continue until mu1 and mu2 reach equilibrium. And we say that the physical interpretation of chemical potential is the tendency of a system to give up particles. So let me write that down. So chemical potential mu. So chemical potential is the tendency of a system to give particles. Now, as all good physicists, we now have to give units to all of our values. So what are the units for temperature? Temperature, the units are Kelvin. For pressure, the units are Pascal. And for chemical potential, a new unit called Gibbs is introduced. And Gibbs is defined as joules per mole. So very simply, I can put all of these in a table and I can write these as this. So this table basically summarizes the important things for equilibria. So for the first one, we have thermal equilibrium. The exchange quantity is energy. The thermodynamical variable is temperature. Units are Kelvin, and the formula is ds over du equals 1 over t. For number 2, mechanical, we have the exchange quantity that is volume. The variable is pressure, and the units are pascals, and the formula is ds over dv equals p over t. Number 3 is diffusive equilibrium. The exchange quantity is particles. The variable is chemical potential. Units are Gibbs, and the formula is ds over dn at constant u and v equals minus mu over t. Now, before we move on, I would like to show you how to derive each of these formulas. So I'm going to give you the mathematical descriptions of equilibria for all 3 of them. So let's do that.